Good afternoon. Welcome to my talk for this year's virtual conference. I hope you're watching this by the side of the pool or maybe even on the beach, kicking back, enjoying the virtual format of this conference. I'm happy to talk to you today about our work on MIMO shaker testing. Let's dive right in. So real environments are multi-axial. There's almost always motion in multiple directions, and that can include rotations if we're talking about a point. Here are some examples, this missile, these missiles. Here, for example, the thrust could be mostly on axis, but aerodynamic forces and lots of other things can cause significant off-axis motions. And um, Often when we reproduce those environments, we do it on shakers that only move in one direction. When is that okay? When is it not okay? And what can we do if we need better fidelity? We were lucky enough in this work to have a nice set of data to work with. Kansas City National Security Campus worked with a university that does launch sounding rockets. And they built a dummy unit that has some interesting dynamics that was mounted inside a rocket and then flown, and they were able to measure the acceleration at several points. So we'll use this as our case study as we think about environment reconstruction. So again, the rocket launches, it coasts, it reaches its highest point of flight. You can kind of see that there. This is the height. So it coasts, and then a parachute deploys and it floats to Earth. So we use data during this boost and ascent phase. Okay, but more on that later. So in this case study, you see an interesting thing. If we take our dummy unit, our component of interest, and we want to reconstruct the environment, we'd have to put that on a shaker. And the stiffness of this bottom plate of the dummy unit will change when we mount it to a shaker. So that changes the impedance. And that can change the way the part responds and whether failure happens in flight or on the shaker. And that occurs because this plate has some natural frequencies that are within the frequency range of interest. And so it has some flexibility that can't be neglected. And this is even worse if we think about testing in other axes. For example, this is to test in the radial direction. We'd have to mount this on some kind of fixture or cube. And so the flexibility changes and the possibility that we might excite some dynamics differently on the shaker than we experienced in flight. And so this is what I mean by impedance, and this is what we're thinking about in this work. So suppose we have this problem, how can we improve the fidelity of our test? So I showed you a picture of a single axis test. One thing we could do is we could mount this on a rigid 6 degree of freedom shaker, and that would at least get the environment in all 6 directions and reconstruct it simultaneously the way it does in flight. But there are limitations there as well. The shaker head will be rigid only up to some frequency, and that might not be high enough for what we're interested in. So what do we do if even that isn't an accurate enough approach? Well, there are two methods that we've been working on. The one that we're responsible for we call the multi-input, multi-output transmission simulator, IMMAT or IMAT method. And basically the idea is that we would take measurements as the vehicle is flying, and that we would take some part of the structure or some fixture, and we'd call that our transmission simulator. And we consider it to be the interface between the body of interest and whatever's carrying it. So in this case, that's this plate, right? That we call that our transmission simulator. And one reason we do this is because if we can completely characterize the motion of this transmission simulator, then we should exactly reproduce whatever happens to the body, because any forces that come into the body have to come through that transmission simulator. I guess we should say any forces except acoustic forces. There could be other forces coming in from other places. So if we were lucky and this plate was rigid, then the transmission simulator would add 6 degrees of freedom. We could use a 6-stop shaker and everything would be fine. If we have some flexibility, we can add a few additional sensors, a few additional control degrees of freedom and try to control to those as well. So that's the idea behind the transmission simulator method. This was really inspired by some work of De Boer, Roberts, and Ewens, who invented the IMAT approach. And the difference between IMAT and what we're doing is that in IMAT, you would also put accelerometers on the body. So you basically test the whole vehicle. And then whatever part you're testing in the lab, say it's this part, you would control to all of these accelerometers and replicate the environment. And this obviously has some advantages, though in some cases it's difficult to do this. It requires having some measurements on the body and that you have flight data on your body plus your transmission simulator, right? If you change the body of interest, if there's a design change or you have a new component, then that data may not be accurate anymore. So what we try to do in our approach is just replicate the environment on this interface fixture, this transmission simulator, and use that to reconstruct everything. All right, so why does impedance matter, though? Why are we making this fuss about it? We can see in a case study. This is a single-axis shaker test on our component here. And if we pick an accelerometer on the plate here and we control to it and we're exciting in this direction, we can get a single input, single output controller to match the response really pretty well on that point. If we get to higher frequencies, it begins to break down because there are resonances in the fixturing and everything that cause the controller some heartache. So we'd have to notch those out or do something there. But in this lower frequency range, it works well. But notice what happens if you look at other points on the test and how they compare to flight. These two are radial directions, so they're in roughly the same direction that we're controlling to. And at these other channels, we can get a big overtest and run into problems. And in the directions, obviously, off-axis, we're definitely not going to reproduce what happens in the real environment. But even there, we can sometimes get overtest, or we might break the part off due to an off-axis motion that didn't actually occur in the environment. So this is why we care about impedance. So our question is, can we design a MIMO test that will do a better job than these traditional single-axis tests? One thing we've used in designing the test is a simulation of what the test is before we do it. And that's one of the principles of IMAT, is to use simulation to make the test smarter. So here we did a roving hammer test on our component of interest, tested at many different points. And then we said, let's suppose that any of these points on this base plate is a place we could attach a shaker. Let's simulate a MIMO test using different combinations of shakers. So to do that, basically, we have this equation that relates the environment of interest to the forcing that's required to replicate that environment at a set of shakers. And these H's are just the acceleration transfer functions between the acceleration and the force. So we can, knowing the environment, we can solve for the forces using this equation. Then we can go and reconstruct what would happen if we apply those forces. And in this case, we can reconstruct the response at every point and see if we control to these 6 points, how do we do with the rest of the points, and so on. So we use this simulation heavily to try to design our tests. One thing we did in all of this is an error metric, and here's all the math, but basically this is just the area between the two curves, between the green, say for example, might be the environment that we've reconstructed, and the black might be our target. And so this is the error in dB, or the area between the green and the black curves averaged over frequency. So it gives us a number in dB that gives us an idea of how well we're matched the target environment. All right, so basically our approach was we have a set of points that we might control to. We pick one of them and we simulate MIMO control using just that point. And we do that for every point on the plate, and whichever one gives us the best match between the target and the control profile, we keep, and then we go and add another point. And so doing this iteratively, we come up with the 6 points that we can use with our 6 shakers to most accurately reproduce the environment. So here's what we came up with. The algorithm decided to put 3 shakers in the launch direction, and here we're using these Q-source shakers by LMS. They're small, lightweight. They don't require stingers, but they typically hard mount to the structure and you push against the inertia of the shaker itself. And then the algorithm also said you need 2 shakers radially and 1 in a tangential or spin direction. So these are all low force level shakers, so we're not going for really large environments, but just testing out the concept. And we'll divide our responses between the stool, or the component of interest, and the plate, which is what we're controlling to. So in doing all of this, we have a set of field data, and we run the MIMO test. We assemble everything and actually run this. These are the 7 accelerometers down here on the plate that we're controlling to. And you can see that we do usually a pretty good job on those control channels. We have 7 control channels and 6 shakers, so we can't do a perfect job, but we do a pretty good job. And we have about a 9 dB average error on those sensors. But if you look at the stool, even though we've matched the response pretty well on the plate, that doesn't necessarily translate into having a good reproduction of the environment that that stool is experiencing. So there's some sensitivity between the motion of this base plate and the motion of that stool. And so it's quite a bit more challenging to get that to match. So this was our first case. To put that in perspective, though, I guess we should also show the green is what we got on the plate in these 7 control channels using the MIMO test. The black is the target environment. And the red is what we would have gotten if we did a single axis control just to this channel in the launch direction. So if we do single axis control, we get pretty good matching of those environments in that launch direction, though not quite as good as we get with the MIMO test, especially when we get to higher frequencies where we have resonances of the assembly or of the shaker system. And then, of course, with a single axis, we have dramatic undertest at most frequencies off axis from the launch. So even though our results weren't quite as good as we might have wanted, they were better than we might have in a single axis test. But we asked ourselves what could be going wrong, what might improve this, and one of our interests in having a transmission simulator was to try to replicate the impedance that this stool saw, the boundary condition that it saw when it was flying. So we looked back at what was actually flown, and we asked ourselves, maybe we should include this plate as well as part of our transmission simulator. Right? Maybe we should do a test where we expand that out a little and we try to match the boundary condition even better, match that impedance better. So we repeated everything using this, using that extra interface plate, and found an optimal set of shaker locations again using the same approach. And we tried to reproduce the field data, and these results are in a similar format. On the plate, we have pretty good control, a little better than we had before. And the results also improved a little bit on the stool. This set of slides compares everything This compares the autospectra averaged over all of those plate accelerometers, the control channels, and then these are the accelerometers averaged over all of the stool or on the component of interest. And comparing the green and the cyan, you see that adding that interface plate, the cyan, drove down the error quite a bit, quite significantly. So we added some more structure, we maybe improved the impedance mismatch, and the results got better. You can see all of that numerically here. So this column is the result with the interface plate, without the interface plate, and with it. So the impedance match gets better. And then these are some numbers for a single axis test. It gets tricky to compare because you're only controlling one channel and all the others may or may not be relevant if they're off axis or not. And we broke it down between a lower frequency range test and these higher bandwidths, which is one of our goals, is to see if we could reproduce the environment to higher frequencies. So we do notice that the errors do seem to decrease a little bit as you improve the impedance mismatch, and then we get a little better control. So that made us wonder, what if we had a perfect impedance mismatch, or impedance match? We didn't have the ability to bring the whole rocket in the lab just yet. So what we did is we took just this component and we made an artificial environment by impacting this bottom plate at random times and in random places with a bar, with a hammer that had been tuned to try to give a 0 to 5,000 hertz frequency bandwidth. So we used that, we created an environment profile, and we reproduced the response, and now you can see the numbers for all the cases. So the impedance match is getting better and better. And interestingly, we did get quite a bit better control when the impedance matched near perfectly. And in all areas, the accuracy went up or the error went down. Now, there still was some impedance mismatch because when we did the test, we didn't have the shakers attached, and we did have to attach those for the environment reconstruction. So we say this is near perfect, but it does seem to support this idea that the better the impedance, the better the control will be. Just quickly, I'll also mention that we've also looked at simulating all of this. So we're using simulations to place the shakers. We asked, could you also use simulations to predict whether one of these tests will be more successful than another? So we used modal test data, measured FRFs from 3 setups, the ones you've already talked about, with just the stool on the plate, with the interface plate, and then that perfect impedance match case. And we performed simulations to see how well we would do. So what those simulations told us, these are the numbers we looked at earlier from the actual experiments where we actually tried to do a MIMO test. When we do the simulations, we see a few things. First of all, the plate errors go way down. So there's a little bit of a gap between what in simulation the level of control we could obtain on the plate and what our MIMO control software is actually able to obtain. And we still don't exactly know why the MIMO controller struggles a little bit to get the same level of accuracy that it should be able to get. So that's some work in progress, but interestingly, if you look at the stool, or this idea of matching at one point and transferring the response to another point, the simulations actually do quite a good job of predicting the level of error that you'll have in the places that you aren't able to control to. And so we think that this could be a useful tool for designing tests and deciding how much of the structure to use as your transmission simulator and whether you'll be able to get a good enough environment at the points of interest. So just to conclude, I think we're learning some interesting new things about the role of impedance and how that affects our ability to reproduce an environment. We know the limitations that single-axis testing has, and we have shown some MIMO tests with pretty significant results. So we think that this could be a valuable method, but we're still studying what level of impedance match is optimum, and are there other factors? Adding that plate also adds mass. Could the mass be more important than the improvement in the impedance? And are there ways that we can quantify impedance to better design transmission simulators and to design these types of tests? In the coming year, we're also looking at using finite element models to predict the MIMO test and to see, can we predict what we would have got here if we had a finite element model that's reasonably accurate. So with that, I thank you for attending my virtual talk. I want to thank again my co-authors, Matt Tuman, an undergrad student at UW-Madison who did all the work here almost, and Washington de Lima and Eric Dodgen at Kansas City National Security Campus who made this work possible. So with that, I thank you, and I look forward to taking your questions live at the conference.